Hello, my name is Lee Klum, and I'll be presenting the maneuver types and low thrust slides. While we are certainly more than comfortable using impulsive maneuvers for our purposes, this does not necessarily mean that we can immediately rule out the use of low thrust maneuvers, because low thrust can be more efficient in terms of propellant usage than impulsive maneuvers, which would mean that we can take more mass to our parking orbit at geostationary. To iterate this point, I created a plot of circular to circular low thrust delta V compared to the optimal delta V, which is a Hohmann transfer. And for a scaling of 10 to the fourth orbit radius, which means a final orbit 10 to the fourth times the initial orbit, the delta V is only about 2.3 times as much. All of this is at the expense of maneuver time, however, so there is a trade-off that needs to be explored. I started with an analysis of low Earth orbit to GEO, as this would increase our payload mass by almost 50,000 kilograms. Calculating the delta V required for a Hohmann transfer, as well as an approximate of the low thrust delta V required, I found a difference of only 0.5 kilometers per second, which means that this would be very favorable to us if the maneuver time was reasonable. Using Astrogator and STK and optimizing the direction of the thrust vector to minimize time, I found that after 50 years of propagation, the orbit had barely even moved from low Earth orbit. This means that the total maneuver time would take somewhere on the order of hundreds of years, which is well beyond the scope of a single propellant depot. I then moved on to a GTO to GEO transfer, so we could then bring about 12,000 more kilograms to our parking orbit. Since GTO is an inclined orbit and we want to get to GEO at 0 degrees, I broke this maneuver up into two scenarios, using low thrust to execute the plane change, or relying on the launch vehicle to do it for us. If we execute the plane change as shown in these two graphics here, the orbit trajectory becomes very complex, with inclination, argument of perigee, and right at center of the ascending node all varying quite significantly. Now, while these orbital elements are changing though, the eccentricity and overall semi-major axis, which gives the shape of the orbit itself, does not change that much, which means a little progress is made after 15 years towards GEO. If we rely on the launch vehicle to do the plane change for us, then similar to the LEO to GEO maneuver, the inclination stays the same, so the orbit trajectory in this case is a lot cleaner than the last slide. However, the orbit simply cycles orientation from 0 to 360 degrees without ever really circularizing at GEO, as illustrated in these two graphics. So after 15 years, there was only slight progress made. As such, we ruled out the use of low thrust, as the maneuver times are well beyond the scope of our projected mission lifetime per propellant depot.